Where a wave of light moves from a medium with a higher refractive index, n1, to a medium with a lower refractive index, n2, the critical angle can be calculated as the inverse sine of lower refractive index divided by the higher refractive index. Different media with different refractive indices will have a different critical angle. As long as the medium that the light ray is travelling into has a lower refractive index than the medium it is leaving, this relationship remains true. This means that you can make light stay within a length of glass, as long as the angle it enters the glass is above the critical angle. This is called the principle of total internal reflection, and is the basis of fibre optics. An optical fibre is one where the combination of materials, usually a core and cladding, is such that the refractive indices of the materials generate a fairly low critical angle. This means that the light will reflect when it hits the boundary, and so stay within the fibre. As long as the cladding has lower refractive index than the core, the light will stay within the core. When you keep the angle above a certain level, you can adjust your fibre to have more than two different materials inside. The core is the same for all fibre types. However, you can change the nature of the path of the light inside an optical fibre by changing the transitions between refractive indices. If you have an abrupt change from one refractive index to another, you create a step index, where the light signal will stay within the core layer of the fibre. This is a way of decreasing signal loss and increasing the amount of information that can be sent down optical fibre. However, if you have beams of light sent down the optical fibre at different angles, they will enter the fibre at the same time, but leave at different times, as they have taken journeys of varying lengths within the cable. This can be overcome by graded indexing, where beams that are travelling at a steeper angle within the fibre can be made to travel faster, and so enter and leave the fibre at the same time as the slower moving waves. Communicating using optical fibres is superior to other forms of communication, such as copper wire, as the clarity of the signal in an optical fibre is clearer than that passed down an electric wire. Copper wire uses large pulses of electricity to send a message. The electric pulse can leak from the wire and lose signal integrity. A light pulse suffers from this problem much less. This means that an optical fibre system requires less relay stations and can send more information in a single strand of cable than a copper wire. Optical fibres are also very thin, meaning that they can be forced into the body without causing damage. Light can be sent down one bundle, and the image seen can be transmitted down another bundle of wires, so that doctors can see deep within the body without exposing the body to the air and the possible infections that poses.